Chapter 2 covers reasoning and proof. Our objective, 2.1, is to use inductive reasoning to determine a pattern. And 2.2, we're going to write definitions as conditional statements. Inductive reasoning. Inductive reasoning is the process of observing data, recognizing patterns, and making generalizations about those patterns. If I asked you to define inductive reasoning on a test or quiz, I would look for, it'd be 3 points. I'd look for data, patterns, generalizations. Right? Now you probably would want to say observe data, recognize patterns, make a generalization about it. But if you have those 3 words, so underline them or circle them, that's what you need to know about inductive reasoning definition. Conjecture. A conjecture is a generalization made from using inductive reasoning. Generalization made from using inductive reasoning. Yes?
What are the 3 words in inductive reasoning that we need to highlight?
Data, patterns, generalization.
Thank you.
You look at the data for patterns. If you see a pattern, you make a generalization about it. Here's an example of inductive reasoning. Very simple, okay? A scientist dips a platinum wire into a solution containing salt, which is called sodium chloride, passes the wire over the flame, and observes it produces a orange-yellow flame. Usually, oh, I forgot to let these people in. Did you get one? Yeah. All right, good. Usually from a Bunsen burner, the flame is blue. So you pass the wire over there with the salt on there, it turns orange-yellow. She does this with many other solutions containing salt. Find that they all produce an orange-yellow flame. Make a conjecture based on her findings. What could we conclude as a result of observing this? Right.
Salt causes the orange-yellow flame.
Yes. If there's salt in the solution, it will cause an orange-yellow flame. Sodium chloride produces an orange-yellow flame. Yes. Oh, you need the note packet. Yeah. Counterexample. Counterexample is a specific case for which a conjecture is false. Is there a counterexample to all apples are red? Yeah, there's green apples. There's yellow apples. There's other apples are different colors, so that's a counterexample. So that would not be something that we could make a conjecture about, that all apples are red. We're going to use inductive reasoning to find the next 2 terms in each sequence and explain the pattern. So what do you think the next two terms would be? And then the challenging part is explaining why. Anybody know what the next two terms would be? Yes.
16 and 22.
How did you get that?
It increases, the increment increases by 1 every time, and it started at 2. So then it went to 3, 4, 5, 6.
Rather than use increment, let's use difference. Yeah, the difference increases by 1 every time. That's all you need to say. Use mathematical terms. The sum increases by so much, or the difference, or whatever the pattern is. All right, so you know, one thing you can do to help you with these number sequences is look for a difference. The difference between 2 and 4 is 2. The difference between 4 and 7 is 3. We're adding 2, we're adding 3. 7 and 11, we're adding 4. So he saw this data, and then he observed the pattern. So the next one would be plus 5. That's how he got 16. And the next one would be plus 6, and that would be 22. So his pattern was the difference increases by 1 each time. All right, the next one. What's happening here with this sequence of numbers? Working with fractions, a little bit more difficult. What's happening here? All right, let's get a comment. Oh, go ahead, Kayla.
Decreasing by half.
You said decreasing?
Yeah.
Actually, no. Yeah, it's increasing, but it's not by half.
6.
It's what?
A 6.
What?
6.
Yeah, it's increasing by 6. Now, if we get a common denominator, we can figure this out. So we've got 1/6, and then 1/3 is 2/6, right? Get a common denominator. Top. We want 6 on the bottom, so we multiply the 2 by 3. We get 6, and we multiply the top by 3. So it's 3/6. And we've got 4/6, right? So like he said, each time we're adding 1/6. So we would get 5/6 and 6/6. That should be a comma, not a plus. And then we have 6/6, or 1 would be my final number. So all you need to say for that is add 1/6 each time. All right, questions there? Here's the data they give you this time is presented in a graph. So you're the athletic director, you make a conjecture based on the graph. Let's go through these. A, more boys play soccer than girls. Can we conclude that from the graph? No, it doesn't tell us anything about boys, so we can't conclude anything. B, more girls are playing soccer today than in 1995.
Yeah.
Yeah, it actually doesn't go to 2015. It's an old graph, but it's showing the upward trend, right? There's a trend that it's increasing. So if we continued with that pattern, we could make a conjecture that by 2015, yes, they'd still be increasing. More goals are playing than in 1995. So B works. Let's look at the other choices and see why they don't work. C, more people are playing soccer today in the past because in 1994 the World Cup games were held in the United States. Does that have anything to do with anything? No. Number of girls playing soccer was more in 1995 than 2001. You can look at the graph. Here's 1995. It's here. 2001. It's here. That's higher. So that's false. So B is the only one that will work. All right. 2-2. Everybody clear on inductive reasoning? Have I given my restroom example on inductive reasoning? Okay, another example of inductive reasoning you might see in the, if you're out in the public, you did inductive reasoning. Say you're in a foreign country and you need to use the restroom. There's two doors. You can't read. Say you're in France. You don't know French. You don't know which door says men and which one says women. So me being a man, I want to go in the men's restroom. So what I can do is I can watch. And I see a man goes in the door on the left. He comes out. Another man goes in that door. Right? A woman goes in the door on the right. Then another man goes in the door on the left. What I'm observing data, which side the people go in. What pattern do I see? What pattern am I seeing? Men go in the left, right? So that would be my conclusion. The men's restroom is on the left-hand side. That's inductive reasoning. All right, conditional statements. A conditional statement is a logical statement that has two parts, an hypothesis and a conclusion. For a conditional statement, it's an if-then form. The hypothesis is the part that follows the if. That's what you're proposing. If this condition happens, so that's what we know. Your conclusion is after the then. What we conclude is this. What's after the then? Hypothesis is after the if. The conclusion is after the then. Everybody have it? Rewrite the conditional statement in if-then form. Here's the statement. The car runs when there is gas in the tank. How could I state this as an if-then statement? Go ahead, Sarah. Or Sydney.
If there's gas in the tank, then the car will run.
Yes. If there's gas in the tank, then the car will run. Don't forget your then. A lot of times people put if, but then they just say, there's gas in the tank, the car will run. You need to have the then included in conditional statements. It is a deduction if you don't put the then. Someone make a conditional statement out of this one. Chapman.
If there are 12 eggs, then the carton is full.
Okay, that'll work. If they're, okay, they did it the opposite way, but it'll work either way. This says if the carton is full, then there are 12 eggs. But, you know, you could have said it, also you could have said if there are 12 eggs, then the carton is full. So either way, it works. It's true either way. We call that a biconditional. We'll talk about that in a minute. Not always is it true both ways, but in this case it is. Negation. Negation simply means you make the statement opposite the original statement. So, a negation, you add not to the conclusion. You may want to make a note of that. So, you would add not to the conclusion. If there's gas in the tank, then the car will not run. I negated that statement. It's not true unless there's something wrong with your car, but that makes it the opposite meaning. Just by adding not to the conclusion. That's negation. Converse. You interchange. Like we did with that egg statement. It was interchangeable. Right? So you interchange what's after the if with what's after the then. The hypothesis becomes a conclusion, and the conclusion becomes a hypothesis. Inverse. You negate both the hypothesis and the conclusion of a conditional statement. If there are not 12 eggs, then the carton is not full. That's an inverse of the egg statement we had. And that's true. We're assuming all cartons hold 12 eggs, but yeah, so you just add not to both the beginning, after the hypothesis, and the conclusion. The last one, contrapositive. You write the converse, then negate both the hypothesis and conclusion. So you interchange the hypothesis and conclusion and make both of them not. Now these terms are difficult to remember. You will need to know how to do these things on the test. What the converse, inverse, and contrapositive is. Not the definition, but actually making the statement. It'll ask you for the contrapositive of a statement. Okay, you need to know, okay, I switched the hypothesis and conclusion, make both of them not. So make sure you understand the difference. You'll have practice in class and on the homework. Hopefully by doing that, you'll be able to remember better what each of these terms means, tells you to do. Any questions? So we're going to do an if-then of this, then an inverse, and a contrapositive. What could an if-then of this be? Yes, go ahead.
If you play soccer, then you're an athlete.
Right? If you play soccer, then you're an athlete. They used if you are a soccer player, then you're an athlete. Let's use that one so we're consistent with our notes. So if you are a soccer player, then you are an athlete. That's the if then. What would the converse of this be? Sydney?
You are an athlete if you play soccer. If you're a soccer player.
No, the if always comes first. Say it again.
If you are an athlete, then you are a soccer player.
Yes, that's right. If you are an athlete, then you are a soccer player would be the converse. Inverse. What's the inverse? Ryan, what's the inverse?
The inverse is you are not an athlete and you're not a soccer.
Okay, the inverse goes back to the original statement. Go ahead.
If you are not a soccer player, then you are not an athlete.
Yes. The inverse would be if you are not a soccer player, then you are not an athlete. Then the contrapositive is what Ryan said, okay, is when you exchange, you do the converse, and then you put not and not. So we take this converse statement, we add not an athlete and not a soccer player. It doesn't matter which order you do it. You can have the nots first and then do the converse, or you can do the converse first, then add the nots. Okay, either way, you're going to come up with the contrapositive. If you are not an athlete, then you are not a soccer player. Any questions? Biconditional statement. A biconditional statement is a statement that contains a phrase, if and only if. Can be used with both a conditional statement and its converse are both true. So this is two lines are perpendicular if and only if they intersect to form a right angle. So let's change this to if then. What would an if then of this read? It's biconditional. If we change it to an if then statement. Bobby, what do you think the if then this would be?
If two lines are perpendicular and they intersect to form a right angle.
Right. And that's true. What would be the other if then we could write from this conditional? What would be the converse that we could write? Yes.
If they intersect to form a right angle, then the two lines are perpendicular.
Right. I would say if two lines intersect rather than they. If two lines intersect to form a right angle, then they are perpendicular. So that's the converse of this statement. Both of those things are true. If they intersect to make a right angle, then they're going to be perpendicular. So both of those are true. So I could make, if I know that, then if I know this is an if and only if, I know both this statement and that statement are true. That's a biconditional. The if and only if means that it's true either way. Questions? Who needs more time to write? All right, I'll leave it up there. Everybody have it now?